Welcome to the wonderful world of solving quadratics, ladies and gentlemen. So we're going to blow through a few quadratics here. Should be stuff that you know, but maybe you forgot some things along the way. So we're going to solve this one here. 3x squared equals 4. What do we do? Well, there's a number of ways to solve quadratics. The simplest way to solve this here is to divide both sides by 3, get the x squared alone, and then square root both sides. X equals plus or minus the square root of 4/3, which is plus or minus 2 over the square root of 3. And in rationalized form, remember rationalized form is where we do not have a radical in the denominator. We have this. Any of these three would be acceptable as far as IB is concerned, and mostly as far as I'm concerned also. I would like it very much if you would try to make sure you simplify things like the square root of 4, the same as 2. All right, so let's amp up the difficulty. Notice difference between these two. This one has just x squared, this one has x squared and an x term, and that, ladies and gentlemen, says we can't just isolate the squared term and get and square root both sides. So we could use the quadratic formula. We could try to factor here. I don't know that this one is factorable, but we're going to use completing the square. So first thing to remember is that the leading coefficient has to be 1. So we factor out the 2 from the two terms with x's in them. And I'm going to move the constant term over to the other side. Okay, so now we need to pick a magic mystical number to go right there that will enable us to take this new quadratic and factor it into something squared. And how do we get that? We take the b, divide by 2, and square it. So negative 1 squared is 1. When we factor this bad boy, we get x minus 1 quantity squared equals not 5 anymore because, we added something on here to keep an equation balanced. We must do it to both sides. And we don't add 1 is the crazy thing. We don't get to add 1. What we have to add is we have to add 2 because we're really distributing that 2 onto the 1. So this equals 7. Now we have something squared equal to a number. Now it's just like this problem over here on the left. We divide by 2. So now we have x minus 1 quantity squared equals 7/2. Now we can square root both sides. X minus 1 equals plus or minus square root of 7/2, and there's really nothing we can do to clean that up. I'm going to leave it alone. X is equal to 1 plus or minus the square root of 7/2. And you'll get the same thing using the quadratic formula. Completing the square can be shorter a lot of times, but the thing you want to look for is what that coefficient is. We ideally want that to be even. If it's not an even number, completing the square can get a little bit messy with a lot of fractions, but completing the square will always work with every single quadratic we encounter. So let's solve this one. Whoa, wait a minute. There's x squared and there's p. I don't know what to do. Oh my gosh. Well, let's say factoring is probably off the table. It is equal to 0, but factoring isn't really going to help. Completing the square, what's the coefficient of x? I don't know if that's even or odd. That's just going to be icky. I'm going to use the quadratic formula here. This is a quadratic equation in x, meaning x is the variable that we'd be solving for. My answer is just going to have p in it. So x equals opposite b plus minus the square root of b squared minus 4ac all over 2a. And now we put our values in. So b is p minus 6. A is 3p. C is negative 2. And again, A is 3p. And now we start simplifying. So negative p plus 6, plus or minus. Now, we got to do some cleanup underneath the radical. P squared minus 12p plus 36, and then we're going to have plus 24p, all over 6p. We keep manipulating, keep working, keep grinding away. We now have p squared plus 12p, we combine these like terms, plus 36, all over 6p. And, well, that quadratic under the radical, that's kind of nice. That's a perfect square trinomial. That's p plus 6 squared. So what we have now is negative p plus 6 plus or minus p plus 6. I'll put that in parentheses, over 6p. So what are the two simplified solutions that we have? Since we don't have a radical anymore, we should go a little bit further. So now is when we split apart into two separate answers. Negative p plus 6 plus p plus 6 over 6p. So the p's would go away. We have 12 over 6p. So one solution is 2 over p. The other solution would be negative p plus 6 minus p plus 6 over 6p. So now we have negative 2p plus 0 over 6p, which is negative 1/3. And there's our two solutions. It was a big, scary, nasty-looking problem at the beginning because it had p's and x's, and we freaked out for just a minute, but it ended up not being so bad. There's just a lot of algebraic manipulation. And so here we go, last two problems to solve for this video, and then we are on to bigger and better things. Let's see what we can make of this. Okay, so they're all divisible by 3. Let's go down the factoring road. Okay, so now the quadratic is a perfect square. That's nice. Let's divide both sides by 3. Square root both sides. X plus 5 equals plus or minus 0. But wait, plus or minus 0, that's the same thing as 0. So x is negative 5. This is what we call a repeated root or a double root. It has technically two factors, x plus 5 and x plus 5, meaning we get x equals negative 5 twice as solutions. This root has multiplicity of 2. Second solution, second equation. I'm looking at this one. It's not factorable. Completing the square wouldn't be nice because it's an odd number in front of the x. I'm going to use the quadratic formula. You may have made a different decision than I, and that's okay. One plus or minus that should be a minus 1 minus 4 over 2, 1 plus or minus the square root of negative 3 over 2, and hopefully you're saying, there's no solution to that, and you'd be right. There's no real solution. In the next section, in the next part of this section, we're going to look at how we can classify the solutions as being one solution, no real solution, or two real solutions, simply by using something called a discriminant. We're not actually going to be solving.